Hello everyone, my name is Higgy Park. I'm a Principal Solutions Architect here at AWS. I've been here about 4 years, and 3.5 years of that time, I was in the professional services organization, helping customers build cloud-native applications. And in the last half year or so, I've been a serverless specialist, helping customers build serverless and event-driven patterns. Today we'll take a deep dive on how to leverage AWS Lambda functions as a consumer for Amazon Kinesis data streams. In this session, we'll cover the components that a message will touch as it flows through a real-time ingestion and processing system. This includes how the message or records are routed from producers to streams, characteristics of those streams, Lambda as a consumer to those streams, first in the standard consumption model. Then we look at how a parallelization factor can improve consumption throughput. And finally, we look at another consumption model using enhanced fan-out consumers, or EFO. This is a high-level flow that we'll be covering throughout the session, wherein we zoom in and dive deep on different components. We'll start from the left side with the producers. We'll work our way towards the right through streams, and finally end with the consumers. First, let's take a look at the producers. We'll start with the producers, and examples of those could be a web server pushing logs to some central log aggregation system through a stream. Another might be application servers pushing custom application or business metrics which require real-time insights. An example of that might be a point-of-sale system providing real-time sales data. Another example might be IoT telemetry devices like sensors in a manufacturing facility that are providing real-time analytics and insight into the health of machines or the efficiency of production lines. Kinesis provides two basic API calls for sending messages or records into the stream. The put record call is used when a producer wants to send a single message at a time. The put records call is used when a producer wants to send multiple messages in a single API call. Per shard, the put record call supports up to 1,000 writes per second, up to a maximum of 1 megabyte per second. Each put records call supports 500 records, up to 5 megabytes for the entire request, which could be distributed across one or more shards. Now remember, the per shard limit still applies. We also have the Kinesis producer library, which acts as an intermediary between your producer application code and the Kinesis data streams API. Now producers send messages, which Kinesis calls records. Those records are the unit of data that will pass through the Kinesis data stream, and that includes the partition key, the sequence number, and the data blob. The partition key is specified with the put records call. The partition key is used as input to a hash function, which is then used to route the record to a specific shard within the stream. And we'll cover shards shortly. The sequence number is used if strict ordering is required across the entire application and would be assigned by the client. If it's not specified, the records will be coarsely ordered based on the arrival time within the shard. And of course, the data is the object that's of particular interest in processing. That data will be base64 encoded and will need to be decoded prior to processing. A single record can be up to 1 megabyte in size, keeping in mind the overall limits. So in the case of a 1 megabyte record, a single API call per second for that shard would be allowed. A Kinesis stream is a set of shards where each shard maintains a sequence of ordered records. Those records can be maintained in the stream for a defined retention period, which is by default 24 hours, but can now be increased up to 1 year. If we add up the capacities of each of the shards in the stream, we get the total stream capacity. Now, depending on the requirements of your use case or the application, you then ensure that you have enough shards configured for the stream. Let's take a closer look at the shards themselves. Each shard has a separate read and write throughput capacity. For reads, each shard can support a maximum of 5 requests per second or up to 2 megabytes per second, whichever threshold comes first. For writes, each shard can support up to a maximum of 1,000 records per second or 1 megabyte per second, again, whichever threshold comes first. Let's take an example where we have a stream depicted with 3 shards. As mentioned in the prior slide, the total capacity of the stream is the sum of the capacities of its shards. Here we just multiply the read and write throughput by 3 for 3 shards. Therefore, for reads, the stream can support an aggregate of up to 15 requests or 6 megabytes per second. And for writes, the stream can support an aggregate of up to 3,000 records or 3 megabytes per second. When configuring consumers, you'd normally have to configure them to consume from each of the shards and manage an iterator to keep track of where the consumer is currently reading from the stream. Kind of like a bookmark in a book to keep track of which page you're currently on. However, with Lambda consumers, the Lambda service will configure a consumer on your behalf. The Lambda service will configure a poller on your behalf, which will serve as the intermediate consumer for each of the shards. By default, that poller will make a get records call every 1 second. It will then take that batch of records and invoke the configured Lambda function on your behalf. The event payload of the Lambda function will then contain the batch of records that will need to be processed. So here's an example of an event payload that will be passed to the Lambda function. First, you'll see that there's a records attribute with a list of objects. Each of those objects has the Kinesis payload as shown previously, which includes the partition key, the sequence number, and the data block, among other things. The poller will then send the batch of records to the invoked Lambda function. Let's take a deeper look at the poller. The poller has 3 components. The record processor is the actual consumer of the Kinesis shards and is responsible for making the get records call. The record processor then hashes the partition key and passes those records along to a virtual queue called the batcher. This is where records are stored up for retrieval based on configured polling policies, which we'll cover shortly. The invoker will then get records from the batcher and invoke the configured Lambda function with the records as the event payload to the function. Now we have a few options of how we configure the invocation of those functions. Here's a quick aside on Kinesis consumers. There are 2 different kinds of consumers of Kinesis that can be configured. Let's take a look at those 2 types and see how they apply to the poller as a consumer of Kinesis. First, there are standard consumers, which is the default type of consumer. All standard consumers of a stream share read throughput with all other consumers. For example, as mentioned before, that each shard can support up to 5 requests or 2 megabytes per second. If we had a single consumer, here a processor application, that consumer could use all 5 requests per second per shard and therefore make a request to each shard every 200 milliseconds. Suppose now we had 5 consumers. Here the processor, aggregator, insights, analytics, and inference applications. Each of those would be able to make 1 request per second per shard. Each of the consumer applications would then need to implement a polling mechanism based on that periodicity. This is the poll model done over the standard HTTP1 protocol. In the case where additional bandwidth or lower latency is required, enhanced fan-out consumers can be used, up to 20 per stream. This could apply when you have multiple applications that each require their own dedicated throughput or bandwidth, up to 2 megabytes per second, with an average of 70 milliseconds of latency. Here now, the processor, aggregator, insights, analytics, and inference applications can each operate independently. The consumer also just subscribes to the shard, and the data is now pushed to the consumer from the shard over an HTTP2 connection. It's also important to note that it costs additional to run an EFO consumer, charged hourly and per gigabyte retrieved. Now let's see where those consumer types apply to Lambda. Here is a view of the standard Lambda consumer through the poller. Each shard of the stream has a configured poller which will invoke the configured Lambda function. This amounts to 1 concurrent execution per shard. Those concurrent executions are for a single deployed application, like the processor application in our previous example. The configuration of the relationship between the stream and the function is defined in an event source mapping resource. And let's take a look at how we'll configure that resource. Here's a CloudFormation template with the definition of an event source mapping that will help us walk through some of the parameters that we can use to customize the behavior of the poller. First, we must specify the ARN, or the Amazon resource name, of the Kinesis data stream, from which the poller will then get its records. More specifically, the record processor in the poller that will be polling on this stream. Next, of course, you need to define the function that will be invoked by the invoker. Here you can specify the function name, the function ARN, or even the specific version of the function that you want to execute. By default, the poller will poll the shard once every second. The functions will then subsequently invoke based on that poll. And we can change the behavior of the function invocations with a number of parameters. The first is the maximum batching window in seconds property. This is the period of time before the invoker will get the records from the batcher and subsequently invoke a function. In the configuration defined here, a function will be invoked once every 60 seconds unless another configuration preempts this batch window size, as this is after all only a maximum, not a static window size. Another configuration is the batch size. Here we specify the number of records that the batcher should queue up before the function is invoked. In this case, if 100 records are waiting in the batcher before the 60-second timeout batch window, a function will be invoked. Therefore, whichever condition is satisfied first, that will invoke the function. As mentioned before, a standard consumer has its limitations. Again, it shares bandwidth and throughput with other consumers of the shard. So if another application is also consuming from the same stream and shards, they will have to share the resources of those shards. Here we look at a few examples of how to use the batch size and the maximum batch window in seconds properties and the impact they have on invocations. First, we start with a batch size of 10 and a max batch window in seconds of 60. So in the first example, we see that record ingestion is light. Thus, the batch is not filled to the batch size, and the invocation is then triggered at the max batch window size of 60. In the second example, we see that record ingestion is heavier. Thus, the batch is filled with that batch size, and an invocation is triggered around the 30-second mark. In the third example, we reduce the batch window size to 30 seconds, and the record ingestion is again light, and thus the invocation is triggered at that max batch window size. In the fourth example, we also reduce the batch size down to 5. The record ingestion is now heavy again, and the invocation is triggered after 5 and 10 records. And this happens at roughly the 15 and 30-second marks. Hopefully that clarifies a little of how the two configurations can be used to customize record processing. But what if we wanted to process records faster? If we decrease the maximum batch window size time, we essentially reduce the time the poller batches and waits to invoke the function. This could work if event ingestion is consistent, but also could result in more function invocations than is potentially needed, especially in cases where record ingestion is light. If we reduce the batch size, we reduce the required number of records before a function is invoked. This is something you'd want to balance with how much compute power is required per record that is processed. If we increase the memory of the function, we get proportional compute power to process the records. This is useful if the application is doing fairly heavy computation for each record. And we could also increase the number of shards for more throughput. And this is going to be important when we're considering the read and write throughput overall. But if we're scaling the number of shards strictly for reads, it's quite possible we could be wasting throughput for those writes that would go unutilized. So hopefully this gives you an idea of considerations we may have when we want to think about how to scale. But let's see if there's another way that we can also scale to add more concurrent invocations per shard. Here we enter parallelization factor. This is where we allow parallel processing of records per shard. This effectively allows multiple concurrent executions of functions at the shard level. But wait, you may think, what about maintaining order at the shard level? Don't we have a potential risk of records being processed out of order? And here's where the record processor will route messages to the batcher based on partition keys. This ensures that per partition key record order is maintained. If we zoom out and go back to our previous diagram, with the standard consumer and parallelization enabled, we still have the same requests per second per shard limits, and thus the same polling latency, but what we've done is increased processing power per shard. Here add the parallelization factor configuration. In this example, we set it to 2 for 2 parallel invocations. This property defaults to 1 and can be increased up to 10. Now this is great for standard consumers, but what about those enhanced fanout consumers that we had mentioned before? In this diagram, we configure a Kinesis enhanced fanout or EFO consumer. The EFO consumer sits between the stream and the pollers and provides dedicated throughput and bandwidth to the poller fleet. For simplicity here, I've diagrammed the consumer in front of a single shard, but that consumer applies to all shards within the entire stream. So let's zoom out again and go back to our previous diagram just as a reminder of what the EFO consumer looks like and the push events that get pushed to the poller fleet. Here's a CloudFormation definition for the Kinesis EFO consumer, where you simply define the name and the ARN of the stream to which it will attach. And here the EFO consumer will sit in front of the Kinesis stream. Now to configure the poller to leverage the EFO consumer, we now update the event source ARN to now point to the ARN of the consumer rather than directly to the Kinesis stream. Here we have configured 2 separate EFO consumers. You can imagine each of the consumers to be configured for different applications. So for example, consumer 1 could be doing basic aggregation and writing it out to a DynamoDB table. Consumer 2 could be writing the records out as a Parquet file to S3 for later data warehousing purposes. Regardless of the use case, each consumer has dedicated throughput and bandwidth and has its own set of pollers and function invocations. So in the example above, imagine consumer 1 would apply to all 3 shards and would thus have 3 pollers and 3 function invocations. Likewise, consumer 2 would also apply to all 3 shards and have 3 pollers and again 3 function invocations. So let's build on these concepts. What if we combine both concepts where we give an application dedicated access, but we also want to accelerate shard level processing? Here we have an EFO consumer and we add parallelization factor for record processing. While not depicted, you can imagine consumer 2 also being configured with parallelization factor. They can be configured with the appropriate parallelization factor necessary to process the records for each respective use case. So again, zooming out, here we see the EFO consumer and now with parallelization factor set to 2. And here's the CloudFormation definition of that configuration. The event source ARN points to the EFO consumer and the parallelization factor is now set to 2. For each consumer that we wanted to configure, we would configure a separate event source mapping resource. So in our previous slide with 5 applications, the processor, the aggregator, insights, analytics, and inference applications, we would configure 5 separate EFO consumer resources and 5 event source mapping resources. So why all these options? A standard consumer with parallelization factor may suffice for the use case, wherein a single application processes many records in parallel. An EFO consumer can be configured if multiple applications need access to the stream and have heavy throughput or bandwidth requirements. And if those multiple applications have intense compute applications or operations, those operations can be parallelized further to increase processing capacity. And this is useful information, but let's take a look at what some of this may look like. So here's a screenshot of the console with 3 configured event source mapping triggers on the Lambda function. The first is a standard consumer and is currently enabled. Let's think of this as the processor application. The second and third are EFO consumers and are currently disabled. Let's think of this as the processor application again, and now also the aggregator application. I configured a stream with 4 shards for the purposes of these tests. Here you can imagine a financial services customer ingesting tick data from market data streams. I started the first with a standard consumer, which you can imagine again to be the processor application, and parallelization here is set to 1. That's depicted in the top left screenshot. With 4 shards in my stream and parallelization factor set to 1, I would expect 4 concurrent executions, which is what we see at the 5:15 p.m. timestamp. I then updated the standard consumer with parallelization factor set to 2, and that's depicted in the bottom left screenshot. With 4 shards in my stream and parallelization factor set to 2, I would then expect 8 concurrent executions, which is what we see at the 5:30 p.m. timestamp. At the end, I changed parallelization factor back to 1 before proceeding with the next test, hence the drop back down to 4 concurrent executions. Now I disable the standard consumer, and I enable both of the EFO consumers. Again, think of these 2 consumers as the processor and the aggregator applications, and note that both can be used together. With the tick data continuing to stream into the system, I had 2 EFO consumers running with parallelization factor set to 1. You can imagine that tick consumer 1 is the processor application, and tick consumer 2 is the aggregator application. With 4 shards in my stream, with 2 EFO consumers and parallelization factor set to 1, I would expect 8 concurrent executions, which is what we see after the 5:45 p.m. timestamp. I then updated each of the 2 EFO consumers with parallelization factor set to 2. That's again depicted in the 2 screenshots on the left. And now with 4 shards in my stream, 2 EFO consumers, and parallelization factor set to 2, I would now expect 16 concurrent executions. You'll notice that the jump from 8 to 16 makes a little bump at 15 concurrent executions before finally reaching the full 16 concurrent executions. The simulation that I ran required additional data to be pushed through the system in order to fully push concurrency all the way to 16. And this gives you a sense of the scale and the ability to process data in parallel. Anyway, I hope this was useful and helpful to see some configurations and the impact that they have on concurrent executions of a given function. And I hope this gives you ideas on how you could potentially use this pattern for your own use cases so that you can drive real-time insight and ultimately deliver value to your overall business. Here are some other sessions that you may want to check out that are related to this topic and that may be useful as you try to build streaming and event-driven applications. Thank you for your time, and I hope that this session has been helpful to you. With that, I also ask that you please do fill out the session survey so that we can get feedback on the session on how to make future sessions better for you. Thank you.